recording now. Okay, so coming back to what we were doing, scroll up quite a bit. So we're looking at this algorithm. We are looking at this algorithm. We have a set from 1 to n, and we flip a coin for each element. And if the coin comes up head, we add this element to our subset. So this is the algorithm. So this generates a random subset of this big set. Now we define these two variables, the maximum and the minimum of the set that we created. And we consider this random variable, the difference between the maximum and the minimum. We want to compute the expected value. And somehow in our computation, we'll get that. So when we simplify this expected values, hopefully this will come out. But for now, let's just focus on finding this expected value. So I have this random variable. I'm going to compute this expected value. So what we did, and the first thing that you should really think about is, okay, the expected value of x is the expected value of the maximum minus the minimum. And I can use linearity here. So here, what we use is linearity of expectation, of expected value. So that is the thing that you should definitely think about. And after that, all we've done so far is go through the definition of expected value once again. So we look at the range of our function. So here I said this thing here denotes the range of my random variable, the maximum of it. So this line is just applying the definition of expected value. Now we covered what was the range of it. So what are the possible values for my maximum of the subset that I generated? Well, it can certainly be 0 up to n. Next, we looked at the probabilities. So what is the probability that the maximum is equal to k? And the key here is understanding this line. If my maximum is equal to k, so k is an element from 1 to n, right? So if my maximum is equal to k, it means that for k, I flip the head. So I got head here. Let's say this is position k. But it also means, what else does it mean? So if I got, so for those that just joined, we're doing 6.20. So if I got k in my set and it's my maximum, it means that I flipped the head and I got, I flipped a coin for k and I got head. But it also means that everything bigger than k was not put in my subset, which means that I had a sequence of tails. All the things, all my other flips after my kf1 are tails. And now, what is the probability of that happening? Well, there's two ways to argue it. You either do a counting argument. So you count the total number of strings that looks like this. And you get to 2 times k minus 1 over the total number of sequences that looks like this, 2 to the n. Or you just use independence. So here I don't care about my first flips. I only care about flip k being ahead and flip from k plus 1 to n of being tails. So I have one flip that is head, that's probability of half, and I have n minus k flips that are tails. So that's 1/2 to the n minus k. So that makes 1/2 to the n minus k plus 1, because I have this extra head here. So there's really two ways to argue this. Either way is fine. The idea is once we have this formula for our probability, we just plug it in our expected value. Okay, and now whether or not this simplifies, I have no idea. But let's pause for now, and then let's go check the expected value of the minimum. So now we look at this other variable, but we do pretty much the exact same thing. What is the range of the minimum? How do we check if... good question. So here, you're looking at this, right? So if that's a good question. So disregard the k-1 flip. So maybe I should make a formula. So the point is, this formula is valid for k greater or equal to 1. Right? And I think that's the point that he's making. But again, we don't really even care about k is equal to 0, right? Because it gets deleted in the expected value. But it is a very very good thing to point out. So this is for k greater or equal to 1. And same thing here. Again, why do I not care actually about k is equal to 0? Because in this summation, I multiply the probability that k is equal to 0 by itself. So if k is equal to 0, this whole thing is deleted. But it is a worthwhile thing to say. So thank you for that. Does that answer your question? I think you just pointed that out for me, right? Just to be careful. Okay, thank you. Okay, so the range, we'll pretty much do the exact same thing for the minimum. So the range of the minimum is the exact same thing. It's from 0 to n. Right? I flip a coin for each of my elements from 1 to n. And if it's head, it's in my subset. So if I didn't include any elements, my minimum is 0. Okay, now what is the probability that min A is equal to k? And again, this k here is for some k. So here maybe I should switch this line. I should say for, sorry, I'm just fixing typos or small corrections. This, maybe I should do this after. Anyway, so for some, for 1 less or equal to k less or equal to n, what is the probability that the minimum is equal to k? So what is the key here? So if my minimum is equal to k, what needed to happen? Exactly. It all comes down to, well, here at position k, I knew that this was my last head, because otherwise I would have something bigger. Well, for the minimum, k is the position of the first head. Otherwise, we would have something smaller. So it's the probability that the first head is at position k. And now again, you can argue this in 2 ways. So it all comes down to understanding that now our sequence, instead of looking like this, well, the tails are the other side. So now I have a bunch of tails like this. So it's not exactly the same. It looks a lot like the other one. So in a similar fashion, so how many tails does that make? So here I have k minus 1 tails followed by 1 head. So the probability of that is just 1 over 2 to the k. K minus 1 followed by a head. So in total, k flips that are fixed. So here we disregard the other flips. And that's kind of what I don't like about independence is sometimes you guys get confused about, well, do I need to care about the other flips or not? When you use independence, you don't care. But when you count things, you do care. So it's the slightly confusing thing. Okay, now we can just, again, use this same summation. So here I'll copy this, say this. This is k times this probability. All right, so now what do we do? Remember what we're trying to prove. We're trying to prove this thing. So now we have everything we need to compute this expected value. So how do we move from the expression, the equation that we have, to something like this? How would you move from, so now we have the expected that we have, the expected value that we have is, it should be min, is this summation minus this summation. Actually, I'll just rewrite it. So this minus, so here I'll just plug the two summations at once. So this bracket just means that maybe I'll just, so I avoid confusion, it's this whole thing minus this whole thing. And the summation have the same range, so I can put them together. And they both have a factor of k, so this factor is at the front here. So it's the summation of this big thing. Again, my question now is, how do we move from this summation to something that looks like this? Right? We want to prove that the expected value of x satisfy this thing here. So how do we do that? So if I go back, how will we get an n here? Again, this part is just a bit of math. So if I want an n, what can I do here? So how would I make an n appear from this summation? Not quite. Let's not differentiate. Right? K goes from 0 to n. So what happens if I put k is equal to n? So the last term of my summation looks like this. It looks like n oops, here, n. And now what do I have? So 1 over 2 to the n minus n plus 1. So that's 1 over 2 minus 1 over 2 to the n. So I have a 1, so it's n times 1 over 2 minus 1 over 2 to the n. So that's the last term of my summation, right? Something that looks like this. So again, the idea is to just have something this is true, and this f of n can be any function that converges to 0 as n grow bigger. Okay, so what next? So I want a minus 3. So how would I get a minus 3 here? So here, what do we have? So what does this look like? This looks like n over 2 minus n over 2 to the n. So the idea of differentiating is not bad, but you should not have to differentiate, I don't think. Doesn't k becomes n times n plus 1 over 2? I don't think so. I'm not sure what you're asking here. So do you mean this k here? When I plug in n, all I did here is plug in n, and then I have the rest of my summation still, right? So the expected value of x, I do this properly, is equal to the last term of my summation. And this last term is just this thing here, plus the remaining terms of my summation. So now what I did is I pulled out the last term. Okay, so now what will I do? Well, okay, I want an n, right? So what happens if I multiply by 2? I'll get my n. So that's maybe something that I should do. So let's multiply by 2. So here, well, actually, let's be a bit careful. Let's not do that. So the thing is here, this is not bad, right? This I can just throw in my f of n. This converges to 0 as n grows bigger. So I have my n. Now, how do I get my minus 3? So plug in n in this formula. So this is n times, so 1/2. So this is n minus n plus 1. So this is a half. So I get n times a half. This is this part, minus n times a half to the n. This is this part. So again, now I'm just thinking if there wasn't a much shorter answer to this, and in my head, the answer is yes. But I'm trying to formalize this. So we want a minus 3, right? How would I get a minus 3? Yeah, it is y, but maybe we're missing a point, right? Maybe it's not supposed to be y. Maybe our approach is wrong. No. So just to make a point, this part I don't think would be on your exam. But finding the expected value of x, you should be able to do, right? This part here, you should be able to do. Proving that this can be written as n minus 3 plus f of n, that I don't think. But up to here, both of these things you should be able to do. So now this is just math. And that's the part that we all hate. So again, keyword should, yes, exactly. You should be able to do this. Hopefully you train yourself to be able to do this. yeah. So yeah, it's annoying math. This is annoying math. Nobody likes to deal with this. Like this is like manipulating numbers. And who likes that? It's just annoying. Okay, so what else could I do? Well, I'm desperate. I don't know what to do, right? So why not expand the summation? So let's see what happens if I put in n is equal to -1. So let's look at, when k is equal to -1, what do I get? I get n minus 1 times a half, and now I get, I get, so what does this become? When n is equal to -1, it becomes just to be careful, why am I, it's a half squared, right? So 1/4 minus, and when this is equal to -1, so -1/2 to the n minus 1. Again, think about, here we're doing something silly, okay? And here we're doing something very silly. So this portion that I'm removing every time, so here, this portion here converges to 0, right? So like, I actually don't care at all about this portion. Like this term that I'm getting every time here converges to 0. I don't care at all about that portion, like not that much. Like whatever I multiply, if I put n minus 1 times here, I will still converge to 0. This thing is huge. So if I multiply by n minus 1, I still converge to 0. Okay, so the idea is to work on this first term here. So what happened here? So I get to n minus 1/4, and I'll be maybe a bit careful. This minus 1/2 to the n minus 1. Okay, so now if I played around with this. So I have n minus 2 and n minus 1 over 4. What can I do with that? So try to put this on the same denominator. So n minus 2 minus 1 over 4. Is this equal to? This is equal to n minus 1. What is this equal to? How do I simplify this? Yes, and that would be a very wise thing to do. There's something that we can factor out, that we can just ditch. Yeah, and again, don't worry too much about this question. I don't want to spend too much time on this. But here, really, the idea is you have your summation. If you want to make n appear, well, there's not too many ways that you can make n appear. The only way you can make a factor of n appear is if n is k. So yeah, the part of the question where you should try to get to is finding this expected value. If you did that, that's pretty much good enough. The last part here really comes down to doing a bit of math, which I don't want to spend too much time on. So here this becomes n plus 1, right? N plus 1 over 4. And that's good. It starts to look like this. So again, I will not be spending too much time on this. But the idea is that's something you can do. You can use your friendly Wolfram alpha. Yeah, so the key point is understanding how you got the probabilities. Yes. Yes. So the only thing with the problem, so here there is a slight problem with the Newton's binomial formula. We don't have the n choose k, right? So again, I don't, but just for you guys, if you guys are interested by this, this essentially comes down to find the Taylor series of this function. When you have something like this, you're essentially you have a linear part and the rest converges to 0. That's the definition of finding the Taylor expansion of the function. That's exactly what this question is asking. So essentially, if you were, why is this question important and why am I highlighting this question? Because if you think about the running time of this algorithm, or the, well, not the running time, but the expected value that you get, it's essentially you get something of order n. So it's close to the expected value of this difference is very close to n minus 3, which is big. When you think about it, this is big. Like this part is negligible. The bigger you look at n, this is telling you that the difference between your max and your min is only 3. And if you think about it, it kind of makes sense. So when I look at the maximum or the minimum, so for example, if I look at the maximum, I flip the coin. Now, what like in terms of how far my minimum has to be, it doesn't have to be very far. It could be immediately before, and that has a fairly high probability of happening. Or it could be 2 steps further. That still has a fairly high probability of happening. And then the further your minimum and your maximum goes away, well, this probability becomes smaller and smaller and smaller and smaller. So it makes sense to expect a difference between the maximum and the minimum to not be too big. Anyways, let's stop here for this question. For those math freaks, if you think about another way, and I think there is another way to do this, right now it's off my brain, but I do believe there's another way to do this. We can show this in some other way, I believe. But the main point is get to the probabilities. That's the main point. And again, how did we get to the probabilities? These are the 2 key lines. So the probability that the max is equal to k means that the last head on the k is on the kth flip. So I have a sequence of heads and tails. My last head needs to be on the kth flip, otherwise I would have something bigger. For the minimum, my first head needs to be on the kth flip. Otherwise I would have something smaller. So you're looking at something like this or something like this. Okay, so I want to move away from this question. Yeah, well, we can move on. I think we can move on. So again, don't sweat it too much about the convergence proof. It comes from what we did, but let's not, it shouldn't, I hope not, it shouldn't appear on your exam. Okay, so here, we repeatedly flip the third coin and stop as soon as you get tails followed by heads. Consider the random variable. X is equal to the total number of coin flips. For example, if the sequence looks like this, then X is equal to 8. At the tails followed by head. So we end at tail head. We want to find the expected value of X. So now there's several ways to argue this. So what does this look like? So this looks like a geometric, right? But we have to be careful. Can we succeed on the first toss? No. So it's not exactly like a geometry. Right? So it's not exactly like a geometry because we cannot succeed on the first toss. So here, there are several ways to tackle this. Let's look at them. So how do you guys want to tackle this? Should we use? 1 over 2 to the n times 1 over 4 to the n. It's simpler than that, simpler. So I think you're thinking about a different number here. So it's simpler than that. So here, we did a very similar question, I think, in my office hours. I think I picked some random question, and we did something similar. I think some of you were there. So the idea here is to note that probability that x is equal to 1 is equal to 0. Right? So that's the first thing that we can observe. If I want to stop as soon as I get tails head, then I need at least 2 flips. That's the first thing that we can observe. Okay. So now what next? Well, I'm going to use the definition. Why not use the definition? There's nothing wrong with the definition of expected value. So again, the definition will be the sum over x in the range of x. I take all values x and I multiply them by their corresponding probabilities. Okay, so now what is the range of x? How many flips could I have made until the first time that I get tails head? 2 I agree with, but why n? Why n minus 1? So you said geometric. A geometric distribution. What is the range of a geometric distribution? N minus k. So how many flips could this take? It's quite infinite, right? This could go on forever. And remember, that's key in the geometric distribution. You keep doing something until the first time you succeed, which is pretty much what we're doing here. So here, we can go on forever. So here the range is from range of x is from 2 to infinity. So here, let me just write k, because k kind of implicitly means that we're only looking at integers. So I usually write k instead. Okay, so now we only have one other thing to look at. What is the probability that x is equal to k? So if x is equal to k, what needed to happen? So if x is equal to k, it means that I flipped a bunch of coins, and then on my kth toss, I got head, and on the k minus 1 toss, I got tails. But then do I know something else? What do I know about this part here? Well, if this is the first time that this happens, it means that in all my previous tosses, this did not happen, right? If x is equal to k, it means that this was the first time that this happened. And this ended on the kth toss. So I know that the rest of my sequence does not contain tails head. So this yellow part, oops, maybe I should write something here. So this yellow part here, yellow part, yellow part does not contain tail's head. Otherwise, we would have stopped earlier. Okay. So now, what am I going to say? So again, if you've done some other questions in your textbooks, you're starting to recognize some previous answers. So for those that maybe haven't done previous questions, still go through it. So here, I want to fill this yellow part with something that does not contain tail's head. So I want this to be the first time in my sequence where I have tail's head. So I think maybe the easiest thing to do is to look at the possible starts. So you have two cases, right? It's the probability that x is equal to k. So this probability is equal to probability that x is equal to k, and first toss was ahead, times the probability that first is ahead, plus the probability that x is equal to k. So I'm just looking at two cases, right? So I don't even need to write this. I can just say two cases. First toss is head. So then what do I know about my sequence? Do I know something about my sequence? Does that tell me something? So it's not quite a geometric distribution. It looks a lot like a geometric distribution, but it's not quite a geometric distribution. Why? Because this probability is equal to 0. We cannot succeed on the first toss. So my question is, if I start with, so maybe we look at the easier case. If we start with tails, what do we know about this yellow part? So here I have a tail. What do I know about this part? They're all tails, exactly. So here, if my first is tail, then everything else is fixed. Right? So if the first is tail, then all flips before tail heads or head are tails. Okay, now if the first is head, what do I know? Yeah. So here, the key point is this observation, okay? So again, I know some of you guys kind of remember answers to other questions, especially to another question that we did in the previous final review, right? Here, let's just think about if you did not know the answer, how would you argue this in a nice way? So here, the idea is as soon as I know where I have a a tails in here, I know that everything after that needs to be tails. So what we're going to do is partition this thing with respect to the position of the first tails in this portion of the thing. Okay, so that's the idea. The idea is to note that, okay, if my first guy was tail, then everything after needs to be tails. So if this guy is tail, then everything after needs to be tails until these two things, these two last flips. So here we're going to partition this probability with respect to the position of the first tail in this portion of the flips. And yeah, as you guys will see, it's essentially we'll have a bunch of things happening. So is equal to the probability. So here we will partition this event can be split into several smaller events. So in terms of the following events. So what are we doing? So I'm going to define a bunch of xj. Okay, and xj is what? Xj is the event that x is equal to k, and the we have and we have tail in position j, and or maybe what's a nice way to say this? So I want to say that in the first k minus 2 flips. Okay. Okay, yeah, okay. I think I know what I'm going to do. Okay, so I'll just be careful about my range. Sorry, I'm just trying to be careful about the range that I'm defining these variables. So what I'm going to say is that x is equal to k, and we have and the first tail is at position j. So what are these available position? Well, it's from 1 to k minus 1. So for 1 less or equal to j less or equal to k minus 1, these are the variables that I'm looking at. So this variable is essentially, so it doesn't have to be k minus 2, right? This could be the position of my first tail, and then this could be followed by a head. So I included this t here. That's the only thing that I did. It just allows me to place a bit nicer on the range of k, of j, sorry. J doesn't have, if I did not allow this guy, then I would have to be a bit careful here in terms of the range. So what is the idea is that the probability that x is equal to k, why are we doing this? Well, this is equal to the probability of x1 plus the probability of x2 and so on, right? If this happened, then for sure I had to have a tails at some point. So I'm looking at every possible position for my first tail. I could, either this could have been my first tail, or I could have had a tail before. And so I'm looking at a bunch of disjoint cases. k minus 1. And again, why k minus 1? Because here, this is position k, and this has to be ahead. So I cannot go further than k minus 1 for my first step. And the idea is now these guys are very easy to compute. Probability that of xj, what is it equal to? So now, if I make xj, it means that I know that my first tell was here. So what do I know then? So if my first tell is at position j, then this is all heads, this is all tails. Do we agree with that, or am I losing you guys? Are we agreeing? We're almost done with this question. Okay. So again, the observation is that we stop whenever we got this, right? So if the position of my first tell is here, and I stopped here, well, it means that everything up to there has to be tails. If I had a head here, well, I would not have stopped there. So this whole portion has to be tails, and this is my first tell, right? Here, xj is the variable where x is equal to k, which means that I stopped on roll k and I got a head, and before I had a tail. And the first t is at position j, which means that this is my position j, I have a t here. So essentially I have something that looks like this. And since this is my first tell, then all of these needs to be head, and all of these needs to be tails. All right, so what does that give me? How many outcomes does this look like?
Wait, just to rephrase it, are you asking for whatever position j that we have?
Yep.
You have a t, like you flipped a t, right?
Yeah,
and
exactly.
You're asking for the probability that you will keep on flipping t's until the last flip, which is going to be an h, right?
So actually, it's you're correct, but you can rephrase this even in a simpler way, right? So what do I know about my sequence? How many sequences does that give me? If I tell you that my first tell is here and I have an H here. So do I know this sequence here?
Yeah, it's all tails.
Do I know this sequence here?
It's all heads.
Okay,
so you're gonna have two sequences.
So no, one sequence, right? This is all heads, this is all tails, and this has to be a head. So I'm only left with one sequence.
Okay.
One over how many sequences?
Well, length k?
Yes, exactly. K tells me the length of this sequence here. So and now think again, we're very close to a geometric distribution. This looks a lot like the probability of a geometric distribution. So this is 1/2 to the k. If you prefer, it's 1 over how many sequences are we looking at? 2 to the k. How many sequence gives us what we want? Only one of them. We have to have heads here, we have to have tails here, and we have to follow it up by a head. So this is one sequence over 2 to the k sequences. And that's equal to 1 over 2 to the k. Okay. So now all this to say, now what is the probability of x is equal to k? Now it looks like a geometric series. So why is there only one sequence? Again, it comes down to this. When I'm looking at x is equal to j, I know two things. I know that my first t is at position j, and I know that I ended on k flips. So my first t is here, and I ended on k flips. So how many sequences can happen? So I need to fill in the rest, right? Well, if my first t is here, all of this needs to be heads. My first t is at position j, so everything before is head. Exactly. I'm looking, so here what I did is I split this event in terms of smaller event. Right? If x is equal to k, well, I need to have one tails before at some point. Either it's here, or either it's here, or maybe it's here. But I need to have one tails in at some point. I'm going to look at the position of the first tail, and I'm going to look at every possible case. So what I'm saying here is that probability that x is equal to k, what is it now? It's the sum of these probabilities. So the sum from 1 to, so the sum from 1 to k minus 1, right? K minus 1 of 1 over 2 to the k. And again, we're doing like a very formal approach to prove something that you automatically thought of. Right? You thought, well, this looks like a geometric distribution, but it's not quite a geometric distribution. But we'll get back to something that looks very close to a geometric distribution. So this probability is a summation of these guys. Have you guys seen a formula for this type of summation? The answer should be yes, right? This looks like a geometric series, but instead of going to infinity, we're stopping at some point. There is a formula for that. So one is not for this k here. One is for the j here. J is in the range. So this should be a j. Sorry. So j is equal to that. So good question. So do you guys know a formula for this? So what is the partial sum of a geometric series? Yes. This is 1 minus 1 over 2 to the j divided by 1 minus 1 over 2. Now simplifying this is 2 minus Did I brain fart? Hope not. Break. Yes, break time. Good answer. Break time. Break time. We come back to this.